If we place two positive charges nearby each other, they will repel. They exert this force on each other even though they're not touching. This is very different from other forces we've seen. If I want to push my car up a hill, I have to touch the car with my hands. But these charges can exert a force without touching. The force can be produced across empty space. We call that force the Coulomb force, but sometimes we also call it the electrostatic force or the electric force. We give it this name because this force exists when the charges are stationary and also when they're moving. There's an equation that we can use to calculate how big this Coulomb force is. We call this equation Coulomb's law, and it looks pretty similar to Newton's law of universal gravitation. So what's Coulomb's law say? It states that the force of electric attraction or electric repulsion is proportional to the product of the two charges, Q1 and Q2, divided by the distance squared between them. This distance would be measured from the center of one charge to the center of the other. The value K is a proportionality constant. That value will be given on your equation sheet. K is called Coulomb's constant, and while it's a universal constant that never ever changes, it only applies for a vacuum or empty space. You might find it odd that these charges can exert a force across empty space. And you're not alone. Physicists puzzled over this for many years, and they finally decided something kind of crazy. One of the most pervasive things in the universe we cannot see. It's an electric field, and it's a building block of the universe itself. Space is filled with an electric field. That's why these charges push on each other, because they exist in space, which has the property of possessing an electric field. The electric field is what transmits the force from one charge to the other. Let's take a brief moment to look at this idea. You might wonder what the most fundamental thing is in the universe. What are the building blocks of the universe? Maybe you think it's an atom, but that's not quite right. So maybe you think it's the protons and neutrons inside of the atom, but those aren't fundamental either. So maybe you think it's the electrons orbiting around the outside of the nucleus. Well, it's not that either. And even if you look inside protons and neutrons, it's not the tiny little quarks that are flying around. To better understand this, let's take a short look at part of a minute physics video.
Just as you can at any time, anywhere, spontaneously write down the number 3, and it will mean exactly perfectly 3, as if there were some everywhere permeating 3-ness, always available to produce a 3 at your whim. It's the same case with the electron. There's an everywhere permeating electron-ness called a quantum field, and from that field every electron in existence has been summoned, and they are all exactly electron.
There is a very real sense in which the most fundamental things in the universe are fields. Particles and even forces come from fields. Let's get back to the idea of the electric field and the electric force. Here are a bunch of objects. They all are charged electrically. Maybe some are positively charged, maybe they're negatively. It's a really complex scenario, and they're funny shapes. How could we know what the field looks like in this space? In particular, I'm going to choose this point, and I want to answer the question, how strong is the electric field at this point P? Well, if I were measuring temperature, I would need a thermometer, and I'd place my thermometer here at point P. But to measure the electric field, our thermometer will be a small positive test charge. A test charge is just a small charge that's positive, and you can move it around to wherever you want to test the field. So we've put it right here at point P. How big is this charge? We measure charge in coulombs, and this charge is 3 coulombs big. To figure out how strong the field is, let's measure the force on our test charge. It's 12 newtons. And you might be tempted to say that the field is 12 newtons strong. But here's why that doesn't work. If we used a 2 coulomb test charge, it would only feel 8 newtons. And if we had used a 4 coulomb test charge, it would feel 16 newtons. So instead of using just the force, we define the electric field strength as the force per coulomb on a small positive test charge. In other words, what's the force that the test charge feels? It's 16 newtons. How many coulombs are in the charge? 4. So the strength E of the field at this location is 4 newtons per coulomb. And look at this. If I go back to the 2 coulomb test charge, there's 4 newtons per each of the coulombs. And if I go back to the 3 coulomb test charge, there were again 4 newtons for each one of these coulombs. Drawing these force arrows doesn't make much sense because their size depends on the test charge. Instead, we draw the electric field strength itself. The green arrow is the strength of the field, which is 4 newtons per each coulomb that you place at this point. What do we notice? That E field vector is parallel to the force on our test charge. Let's put this into practice. Here's a giant positive charge. I want to test the field in the area around it. So what do I need to test my field? A thermometer. Whoops, I mean a test charge. So first I'll put my test charge here, and I measure the force. If the force points in that direction, I divide by Q to get the electric field strength. Then I put my test charge here, and I measure the force. And I divide by Q to get the field strength. Then I put my test charge here. Again, I measure the force of repulsion. I divide by Q to get the field strength. No matter where I put this charge, it is going to be repelled. Why? Because the test charge is always positive. And so the electric field strength points away from this positive charge in the middle. What if I put my test charge farther away? Coulomb's law says the farther you are, the weaker the force. So if the force is smaller, the electric field will be weaker. And if I go even farther out, the electric field will be even weaker than before. So at each of these locations, we can fill out the vector arrows to show what the field looks like. Let's take away these E letters. And here is the electric field around a positive source charge. A lot of the time, we don't draw these arrows. Instead, we connect them as solid lines. These lines are called field lines because they connect the electric field strength vectors. What if we change it to a negative charge in the middle? How will the picture be different? The only difference is the arrows point in toward the negative charge. And the reason is because if I put a positive test charge right here, it would be attracted toward the negative charge. The thing to remember is that these field lines show the direction that a positive test charge would be pulled.